The next method we will look at in the module about analysis of large graphs, it's called Trawling. And this is another method that is very scalable and also very nicely uses the material that we have already learned in the class. What's also nice about this method is that it goes and detects very different types of clusters that we have talking about so far. So here is the idea. What we want to do is we want to find, let's say that we are given a big web graph. We want to go find small communities in the web graph, right? So we have the graph where nodes are web pages and edges correspond to hyperlinks. And the question is, what is a signature of a community or a discussion in the web graph? And thinking about this idea that actually comes from the hubs and authorities, we can think that a signature of a discussion or a topic in the web graph is to have this bipartite or two-layer structure, where we can think that we have a set of hubs on the left that point to a set of authorities on the right. So the idea would be that these pages, the red nodes here on the left, they all point to a set of authority or content pages on the right. So what we would want to find is we want to go and find in a big web graph, we want to go identify dense two-layer graphs. And the idea here is that kind of a set of people talks about the same topic. How do we formalize this problem a bit more clearly? The idea is the following. We want to go and enumerate complete bipartite subgraphs K, S, T. So the idea is that I want to find graphs where I have S nodes on the left and I have T nodes on the right. To give you an example, here it is. I have a graph that I call K 3, 4 because I have 3 nodes on the left, and these 3 nodes on the left link to the 4 nodes on the right. Notice that every on the nodes on the left has 4 outgoing edges, 1 to each other blue node. So it's a complete graph in a sense that all the edges are present. Every guy on the left links to all the nodes on the right. And so the important point is that my graph is fully connected. Here S equals 3 because the size of the X equals 3, and T equals 4 because I have 4 nodes on the right. So our goal is to go and identify all the complete bipartite subgraphs with a given S and a given T. Now that we have specified the task, let's think about the machinery we'll be using to solve it. And kind of surprisingly and interesting, the machinery we'll be using comes from the frequent item set enumeration. So let me remind you first what is the frequent item set enumeration, and then I'll show you how these algorithms actually find bipartite subgraphs. So what is the frequent item sets? We have to remember the market basket analysis, where we think of ourselves having lots of market basket data, where we have a set of items U. Let's say that there is n of them. This is basically a set of products we are selling in our supermarket. And let's think that we have a set of baskets M, where the idea is that every basket, every kind of shopping cart is a subset of items we are selling, right? So every shopping cart, every basket S, S1 to SM, it's a subset of all the items we are selling in our store. Then what our user also gives us, it gives us the support threshold, which is simply the frequency threshold F. And our goal, our task is to identify subsets of items T. This we will call frequent item sets, such that these are the sets of items that appear in at least SF of the baskets, right? So F is the support threshold. We say that item set T has a support threshold F if it appears in at least F market baskets, so in at least S sub I baskets that we have, right? Now that we defined and refreshed what do we mean by frequent item set enumeration, the next question is how do we connect the frequent item sets with bipartite graph extraction? The way we think about bipartite graph extraction is the following. What we will do is, given a graph, and for every node we will create a market basket. So the idea is that for every node I define the basket Si simply as a set of nodes that node I points to, right? So if I have a node I here, then the basket I create is, let's call it S sub I, contains the IDs of all the nodes that node I points to. Here they are, right? So I creates a market basket of items A, B, C, and D. And then how can I think about a complete bipartite subgraph K, S, T? I simply think of it as a set Y of size t that occurs in little s sets S sub I. Okay, so saying this a bit more simply, basically what it means is that what we are doing is we are looking for bipartite graphs. It simply means that we are looking for a frequency threshold set to S and look at the layer T, so the right-hand side, for all sets of that given size, right? So if I have a bipartite graph, let's say in this case I have K3, 4, then the idea is that I want to find frequent item sets of size 4, right? This is 4, that have minimum support threshold at least S, which is 3 in this case, right? Because this means that I have 3 nodes on the left that all point to the 4 nodes on the right. So the Y, the size of the right-hand side, is simply the item set size, and the size of the left-hand side is the support of that given set of items. To give you a bit more animated example, for every node I create an item set, simply as a set of nodes that that node I points to. Then I set the minimum support, which is S. This will be the size of the left-hand side, and let T be the size of the item set that I find. So now, if I found a particular item set that I call it frequent, that has, let's say, entries A, B, and C, this basically means that there are at least 3 other nodes, right? Because minimum support threshold in this case equals 3, that there are at least 3 other nodes in the network that all point to my set of nodes A, B, and C, what in turn means that we have now discovered a bipartite subgraph K3, 3, where nodes X, Y, and Z point to nodes A, B, and C. So in this sense, we have found exactly what we wanted. We found a complete bipartite subgraph. Another example, think that I'm given this graph here on the top left corner. From this graph, I generate a set of item sets. Basically, the idea is that for every node, I simply ask what are the nodes this node points to. So node A points to B, D, and C. So I have the item set A to be B, C, and D. For example, node F doesn't point to any other node in the network, so node F has is empty, while, for example, node B only points to D, so here is node D. Now imagine that I go and say that I want to find all the frequent item sets with support threshold equal to. If I do this using, let's say, the a priori algorithm on this set, I find that BD has support 3, and I find that item set S has EF has support 2, which means now that we have found actually 2 bipartite subgraphs, right? I found the set BD that has support 3, which means that there are 3 nodes A, C, and E that point to both B and D, which is the subgraph that I find here. And then the second bipartite subgraph we have extracted has the nodes E and F. Here they are. It has support threshold support 2, which basically means that there are 2 other nodes, in this case C and D from here, that both point to E and F. So this is basically the way how this method works, and how it basically allows us to extract bipartite subgraphs. What is an important point here is that these bipartite subgraphs have to be fully connected, which means all the nodes on the left have to link to all the nodes or to every node on the right.